Всем доброй ночи. Сегодня у нас будет интересное шоу. Посмотрим, что происходит сейчас в обсерватории в Австралии, в Сиднее. Люди собрались, очень много машин запарковано, негде запарковаться во всем районе. Даже проехать по улочкам очень тяжело, потому что очень много машин стоит. Сейчас подберемся поближе, посмотрим, что тут происходит. А люди просто стоят и смотрят, что за события. Я вообще не заходила на их сайт, не смотрела, что тут происходит. Просто проезжала мимо и поняла, что что-то происходит. Возможно, оно уже все закончилось, но проверить всегда есть смысл. Почему бы и нет? Наверное, день открытых дверей тут или что-то такое. Очередь даже стоит. Очень интересно. Hello.
You can get the bread inside.
What is there?
What's in there?
Yeah, what's happening?
They do speeches inside.
Oh, okay.
Where you can line up here and then have a look in the observatory, look through the telescope.
Okay, I will check what is there and come back.
Yeah, no worries.
Thank you. Yeah.
We're not going in?
I think I checked. I would go now. There's only like 2 people in
And above all, it's an awesome pop. Okay, yeah, as I mentioned, primarily for deep space objects, low resolution for planets. If you want planets, that's a different situation. So the as I said, it talks, so you can tell how loud it is. This is your jewel here that will mount. So if you're in cold weather, switch that on. It's got an internal heater that stops the lenses heating up. I've got my Do Not Disturb switched on, which means once it's working, it actually turns all its lights off. And it'll turn the lights back on again when I come out to get it. And of course, you can remotely shut it down and put it somewhere asleep. Would you like to have a look at it? You've got to say yeah.
You know you were talking about the Wi-Fi, so you can use that in pretty remote places with its own Wi-Fi.
It has its own Wi-Fi. It doesn't require the internet at all. So it's got its own web server built. That's the size of it. That's the scope. Now you can use any camera tripod, will fit it. This is the one that comes with it, so it needs to go on a table. But as I said, if you've got a camera tripod, it'll work better.
the old Super 8 cameras.
Yeah.
That's the size they were. And they, you know, like, now we use these Super 8 cameras.
So we'll start the app. So the first thing it does is a Bluetooth connection. We'll just wait for it to initialise. Oh, yeah. And that's what you get. No, I'll demonstrate it here. Like you won't be able to see anything. But if we were outside, yes, it would orient itself and start taking photos. So we can, I'll tell it to open itself up, which is what it's doing now. And this is the scenery mode, so I'll have a look at you, good people.
Will you photograph us?
Yeah.
Can.
Anyway. It's got two cameras in it, so it's running off the top camera at the moment. So we can do a time lapse. So if we run that, you know, as you all walk in, you can do that bit. Or you can have, you know, cars going across a bridge. It will do that for you too. If you want to follow a particular thing, you just highlight it until it's a track, and then it will actually follow wherever it goes. So just stop that for now. So. So at the moment, these are all the things that are available to emit. And I'm going to upset it a bit, but I'll tell it to go to the Lagoon Nebula. Now it's going to go looking for it because, it won't be able to see. But that's what it'll look like. And the graph down the bottom gives me all the details about the nebula. So at the moment, that's actually a good spot to see. I'll just
So that's the angle it's at now, so it's perfectly straight.
It will when I hit the button.
Yeah.
It will point exactly where the Lagoon Nebula is. So tell it to go, guys.
It's talking.
Yeah. Well, what it'll do is actually point in the correct direction, but it won't be able to finish the image because it can't see anything. So it automatically focuses, it automatically adjusts itself.
How does it go in memory?
It's 64 gig of RAM.
Can you clear that at all?
Yeah. You just hook it up to any computer, and it just looks like a flash drive. And you can just download all of the photos. It puts the photos in a folder with the name of the thing that it was imaging. So if it was M8, it would be under the M8. Just download it. Yeah, better tell it to stop, otherwise we're going to see.
Вия, привет, я в обсерватории. Представляешь, тут какой-то прибор показывают, который наблюдает за всем.
So the other thing that you can do with it, which is really cool, you don't have to be connected to the phone to use it. You can walk away from it. Once you tell it what to do, you can disappear. It will go ahead and do its work, and when it's finished, it will close up. But at the moment, I'm going to tell it to. There we go. So that's telling me that it's open. It tells me the battery, what mode I'm running in, because it can run in equatorial mode too. And at the moment now, I'm going to tell it to shut down.
And what's the battery life?
Sorry?
What sort of battery life is it?
Sorry?
What sort of battery life does it have?
If you're not running the dual 6 hours, it's an external battery as well. So you can do this.
Charging is just USB, is it? Is it a separate charger or is it just?
Yeah, USB-C. So all you do one of those fully recharged stuff, it gets right down to 0. Plug that in, plug it in on the side, it'll keep doing the imaging and then it'll charge itself back up again. So, any questions?
Are you giving them away?
If I had them, yeah. But I've actually got a couple of giveaways
Really?
for a couple of questions. Thank you. Okay, so I'll be around if you've got any other questions. By all means, ask. Yeah, that's the S30.
Yeah, thanks very much for that.
Not a problem. By the way, that's the sun filter. So, got to have that if you're going to image the sun.
Hey, Emily, you want to share? Absolutely.
Yeah, that's the S30. Now the S50 has a larger objective, so you do pick up more detail, but it covers a smaller area of the sky. So this will do a nebula in one hit. The S30's got to do it as a mosaic, so I'll do parts of it and put it together.
You happy with that?
Oh yeah.
Yeah, it looks fantastic. I love how it's smart.
It is
So,
good.
what you track and you don't have to be there.
Well, that's the thing. You don't actually need to be connected to it
GPO.
for it to run.
That's great. How many years?
Sorry?
Just buy them online.
Yes, you can.
Yep. And it's been delivered and that's it.
Yeah.
Yeah, awesome.
Well, as I said, I just mail ordered it, got it out of the box, powered it up. It did a firmware update, and then
How long have you had it for?
they were released in February. I bought this one in February. Oh, sorry, I released in December. I bought it in February.
Okay. So you had it 6 months. Great idea.
Yeah, that's okay.
You're going to come and listen to it?
Yeah.
Okay, David. Let me take it off.
You can image it, it just gets a little bit harder. Yeah, just image it. Well, let's go straight off this with no processing. Yeah. The thing is, different times of year, you're actually
If you want to, yeah.
So, how was the universe created?
This way, there was a few abstract. In reality, if you're trying to do it manually, it's a real challenge. Yeah. For us, that's really difficult.
That's all right. Don't worry, Debbie.
Most people really choose that.
Yeah, that's okay.
Well, the problem is,
Don't worry.
trying to do it manually, it's trial and error trying to get through.
All right, so this talk is about how the universe was created, or at least how we think it was created, and what the evidence and the implications for this are. Some time ago, when I was younger, there were two competing theories for how the universe was created. One was called the steady state theory, and that theory was formed on the basis that the universe always existed and was infinitely old. But in order to overcome the problem, as soon as you have something that's infinitely old, then all the energy in the universe would already be used up and then it would just be dark and black. So the only way to overcome that was to have matter being created continuously all the time to replenish the matter in the universe that used up all the energy. Now there's one giant problem with that. There's no evidence that matter was ever created anywhere. No one could ever find evidence that matter was being created anywhere in the universe, because it needs to be created in specific places, not just everywhere. It needs to be created in order that it forms stars and then we have more energy. The other thing that killed the steady state theory was that people started to discover that all the galaxies are moving away from each other. And the further away they are, the faster they're moving away from each other. And this is the same view that everybody would get in every galaxy in the universe. They would all see all the other galaxies moving away, and the further away they were, the more they would move away. And the implication of this is that it would be like an explosion that sent all these moving away from each other. And that's essentially the thesis of the Big Bang Theory, and that the universe was created not infinitely long ago, but a certain time ago was a time when it was born, and it's existed ever since then. And it looks like it was a giant explosion that threw it apart. So we know this because we've measured the speed of galaxies. We can measure the speed of galaxies by looking at their redshift, because the light shifted to the red, the same as when a car goes past you, it's coming towards you, whoa, it goes like that. The light goes the same way. The wavelength increases, and we can tell how fast they're going by taking a spectrum of the light and seeing where the lines of particular elements are and how they're shifted to the red. And so then we can tell how fast they're moving away from us. And people were doing this since Edwin Hubble in the 1920s, but it never got enough traction until a lot of people started working on this and got redshifts for lots and lots of galaxies, and then started working out how far away each of these galaxies were. So the further away they are, the faster they're moving away from us. And everybody's going to see the same picture. Every galaxy in the universe sees that same picture of all the galaxies moving away from each other. So if we take this arrangement of galaxies all moving away from each other and we run the whole film backwards, we find that about 13.8 billion years ago, all the galaxies were in one place. Everything met in one place. And that's further evidence that they all came from one point somewhere. The Big Bang happened somewhere and it created all the matter in the universe and all the galaxies that formed from it. So it must have been propelled away from there in order to see the universe we do. Thus, the Big Bang Theory became the thing that everybody believed created the universe. And it's probably correct that something like that happened to create the universe. The other piece of evidence that people have for the Big Bang Theory is what's called the cosmic microwave background. This was emitted about 380,000 years after the Big Bang. Why so long? Because at this time, its temperature reduced to about 3,000 degrees Celsius, which allowed atoms to form. And when atoms form, then the universe becomes transparent. So that this time was the first time it became transparent, and we can see stuff coming out from there. Now at 3,000 degrees, that light is going to be kind of yellow. It looks a bit like the light from the sun. We've got a yellow sun, it looks a bit like that light. But because the universe has expanded so much since then, the wavelengths of light have been dragged along with the expansion, and now they're much longer wavelengths, and now they're in the microwave spectrum rather than the visible light spectrum. So this is the first time it became transparent, and this is what people see when they look at the microwave background of the entire universe. So it looks like an oval, but you can imagine this bit links up with that bit. It's a way of depicting the whole sky all around us just this way, distorting it this way, of course. Now, the other thing that's important here is this picture, in order to get this structure in the universe, which shows that the universe wasn't exactly even, all even, at this period in time, is you have to magnify this picture 100,000 times in order to get any information out of it. It's so vague a piece of information. So how did they get this picture? Well, they send satellites up there to take this kind of pictures. So the first picture they get is the one at the top here. And the problem with that picture is it contains lots of information that they need to try to remove. The first thing you'll notice is this blue band of light across here. And that's called the zodiacal light, and that's the light of the solar system. That's the light reflected, the sun's light reflected by stuff in the solar system, dust around the solar system, the asteroid belt, planets in the solar system, and then the great swathe of comets that are waiting out in what's called the Kuiper belt. So all these things reflect back the sunlight, and when we look at the sky, and we use a very sensitive satellite, we can see that thing there. So that's got to be removed. So that's not so hard to remove. We can understand what plane it is, and we can try to remove that light, even though it's got lots of wavelengths. So we're left with this. And in the middle of this, that thing in the middle there, that's the Milky Way, because that's where the satellite's taking it from. It's near the Earth. So it's going to take the Milky Way, and then there's the rest of the universe there. So you need to remove the Milky Way. And when you remove the Milky Way, well, you get kind of remnants of it. You know why? Because there's microwave emitters in the Milky Way itself. So you remove the light of the Milky Way, but you end up with other stuff in there that emits the same kind of microwaves as you're trying to find there. So you need to be careful what you remove and what you don't remove there in order to try to get back to what happened after the Big Bang. So this is the picture once you amplify it 100,000 times, but as I said, just wait. Are there foreground things in front of that picture that we didn't remove, that we didn't know were there? Well, certainly, since they launched the James Webb Space Telescope, we know there are lots of galaxies really early on in the universe, much earlier than anybody would have imagined in the universe. And they also have microwave emitters in them. So there's lots of things in here that contribute to this picture that aren't just the microwave background of the Big Bang, but are also foreground objects, foreground galaxies in there. How much do they contribute to this picture? Well, there's a paper published recently that said at least 1.4% of that is the foreground objects, and it could actually be, all of it could be foreground objects. There are so many foreground objects. So it's quite a wide estimate at this stage. No one knows how much of this stuff is really the remnant of the Big Bang, and how much this is contributed to by foreground objects, and the remnants of the Big Bang aren't what people have always thought they were. Now, how did they find this in the first place? Well, there was a couple of guys working for Bell telephone laboratories in the 60s, I think, Penzias and Wilson, they made this giant antenna as a big horn because they were going to do communications. They're trying to transmit telephone signals over the Earth without laying cables everywhere. So they were going to use microwaves to do this. So they built this giant antenna and a big amplifier to detect the signals so that they could get the signals from somewhere else, from lots of telephone calls, and decode them in there. And what they found was they get this hiss out of their amplifier all the time. As soon as they turned this thing on, they got this hiss. And they thought there was something wrong with their amplifier. So they rebuilt the amplifier again, just to make sure it was okay, and put it all together again, still got the hiss. And then they thought, well, this giant aerial, like a horn, must be dirty. So they cleaned it meticulously. And they still get the hiss. And then they started moving it around, and no matter which way they pointed this thing, they got the hiss. And it wasn't until much later when people heard about this, and some scientists heard about this, and said, I know what the hiss is. It's a microwave background from the Big Bang. This is the evidence we've been looking for. And since then, they've actually tried to map it, and they've got this picture from it. Now, the other thing that's a feature of the universe at the moment is this thing called dark matter. Now, there's much more dark matter than there is ordinary matter, stuff that we're made of, right? Stuff that stars are made of, stuff that you're looking at through the telescopes is made of, all these things. We're made of ordinary matter, but the problem is there isn't enough ordinary matter in the universe for some of the things that we see to occur. One of the things is galaxy rotation curves. Galaxies like the Milky Way, that are about 100,000 light years wide, and they rotate. They have to rotate, otherwise they wouldn't exist, they just collapse. So they've got rotational energy. And we can measure in galaxies how fast they rotate, because we can take a spectrum of the light on one side of the galaxy and a spectrum of the light on the other side of the galaxy, and we can tell how fast this side's going and that side's coming, for instance, or the other way around. And we can tell from different places along that galaxy how fast it's coming or going. And it turns out it's rotating too fast for the amount of matter in the galaxy. So there needs to be a lot more matter in the galaxy in order to contain it and have the rotation occur as we measure it. The second thing is gravitational lensing. You can see this one up here, that's kind of a really classic one. So in the middle there is an elliptical galaxy. Elliptical galaxies are really, really large, but there's a giant black hole in that one. In the Milky Way there's an ordinary black hole, it's 4.3 million times the mass of the Sun. But this one is 36 billion times the mass of the Sun. So it's an enormous, enormous black hole. But that's still not enough to bend this. The blue thing around it is a spiral galaxy that is actually behind this, a long way behind this, and the light from the spiral galaxy comes towards us and is bent by that thing, like a lens, and then we see it as a circle around that. That's called a gravitational lens. It works differently to a normal optical lens, but that's what happens. And you can see it's blue because it's got lots of star-forming regions in it which are blue, and that's a spiral galaxy. Here's another one where we've got a cluster of galaxies here, and you can see how everything is distorted around it. Look at that one. And this one down here. There's lots of things that are distorted around it. Now the cluster of galaxies there doesn't have enough mass that we can count of ordinary matter to be able to make that arrangement there of gravitational lensing. You need a lot more matter there, and that's where the dark matter thing comes from. So these are the two pieces of evidence that we have that dark matter must exist somewhere. Now comes the problem. Was dark matter also created in the Big Bang? Because you know the giant atom smasher in CERN is a 27 kilometre round particle accelerator under Switzerland. It's been there for ages. They keep upgrading it to make it more and more and more and more powerful. At the moment it's so powerful that the collisions it makes are the same as the universe made 1/1,000,000th of a second after it was created. And 1/1,000,000th of a second after it was created, the universe consisted of a quark-gluon plasma. And we'll come to quarks and gluons later. But it's a very, very dense state of matter. It's even denser than protons and neutrons because these are the constituents of these particles. So the other thing, scientists have, and we've had them come here and talk about this stuff. Oh, we've got to spend X million dollars building this detector. We think we might be able to detect this kind of dark matter or this other kind of dark matter. And they've built these detectors all over the world to detect any species of dark matter particles that they can imagine exists, and they've come up with a 0. None of the dark matter particles that they thought existed have been detected by any of the detectors that anybody has ever built. So there's two problems here. One is, was it dark matter actually born in the Big Bang or not? And secondly, why can't we detect any of it when we see the gravitational influence of it? Now, if people tell you they understand how the Big Bang worked, ask them about that, because they don't know how it worked. So what are the consequences of thinking about this Big Bang thing? Well, the first consequence is, where's all the antimatter? So if we have an energy source and it creates high energy photons, and photons go along, the photon can divide into two particles. It always divides into a particle and an antiparticle. They always just do that. They never create one or the other. So if a photon goes along, it creates an electron, which we're all familiar with, and a thing called a positron, which is an electron with a positive charge. It's the antiparticle of the electron. As soon as you create those two, they attract each other like crazy and they annihilate, and you end up with the photon going on again. So the problem is, there is no process known to man that creates matter alone instead of matter and antimatter together in order to give us the universe that we see, because we're all made of matter. None of us are made of antimatter. If this wall was made of antimatter and I touched it like that, there'd be an explosion that would blow up all of Sydney. So big as any atomic explosion that's ever occurred. So there's no presence of antimatter anywhere that we can see, because otherwise we would see the effect of matter and antimatter annihilating each other in the universe. So this is one major problem that they just hand wave away. Oh, it must have been some process because we've got all matter. We're all made of matter. Well, it might be some process, but there's no process known to mankind or physics that does this. The second thing is the universe a black hole? So there's a theory that we live in a universe that is itself one enormous black hole. And it's difficult to think that this could be unavoidable in any way. I think the universe is going to be in a big black hole, because when it was made, all the matter in the universe was contained in something the size of a pea at once. 1 millisecond, 1/1,000,000th of a second after the Big Bang, all the mass of the universe was created in something the size of a pea. There's no way you're going to stop that making a black hole. So this is a consequence of that. And if we think about the various forms of matter that we have, this can be somewhat instructive. When we look around us here, we all see normal matter. Atoms. We're all made of atoms, mostly hydrogen, even though you don't realise you've got a lot of hydrogen inside you. Various other atoms. Now, most atoms are all atoms are completely empty space mostly. If we take a hydrogen atom, which is one proton in the middle and an electron orbiting around the outside, and we magnify it a lot so that the proton in the middle becomes the size of a pea, then the electron will be more than a kilometre away, just for hydrogen. So then the rest in between, the little proton and the electron more than a kilometre away, is just empty space. There's nothing there. Now, when the sun eventually runs out of fuel, it's going to start. And the Earth, one tiny little thing over there, well, the sun is going to be about as big as the Earth when it becomes a white dwarf. It'll be very hot and it'll be very dense, but it'll be very small. And it will rotate in about a minute. Whereas now it takes days to go around. It'll take about a minute to go around when it's a ball like the Earth. Now, to be a ball like the Earth, there's too much mass in the sun for atoms to survive that process. And so what happens is in these white dwarf stars is atoms become jammed together so hard that the electrons are forced away from their orbits. So we have lots of nuclei.
Это я в обсерватории пытаюсь понять, о чем они говорят.
So it's a much denser state of matter than anything we have. Much denser than lead, much denser than anything that we have. Now, if the sun had a little bit more mass than that, even this form of matter wouldn't hold it up from its own gravity.
Там про черные дыры, про антиматерию.
To be what's called a neutron star, which is just made of neutrons. So all the electrons that are flowing around, the gravity would eventually squeeze them so hard that it forces the electrons into the protons and they make neutrons. And so the whole star, instead of being the size of the Earth, would now contract to be the size of New York City. It would rotate probably 100 times a second. And it would just be pure neutrons. Now, go back to how much empty space is in atoms.
Ты лучше напиши, что у тебя там родители вернулись.
One teaspoon, if you could take 1 teaspoon of neutrons, it would weigh as much as Mount Everest. And that's how much empty space is in the atoms in Mount Everest, because the nuclei fit on 1 teaspoon. Well, it's incredibly heavy, no one could hold it up. But it's so something much denser than that forms neutron stars, forms black holes. And lots of stars, really large stars, when they explode as supernovas, form black holes, leave black holes behind. Because a neutron star won't even hold that up. The gravity is so strong. So if a star can form a black hole, imagine if we had the whole of the universe the size of a pea, how are you going to stop that going into a black hole? It seems unavoidable. I think our universe, although we don't consider this, we live inside of a universal-sized black hole. It seems unavoidable.
Короче, мы в дыре живем, в черной, и вот и все. Все наши универсы.
Are there other universes? Well, if you create this one 13.8 billion years ago, from nothing, it just goes poof, and suddenly all the universe is there, then it would be just as easy for other universes to get created all the time. There's one created right now. It's just got different dimensions to us. We can't see it. It may have different physical constants to us. It may not be able to form atoms. If the charge on the electron is slightly different, then it can't form atoms. If any of the other physical constants are slightly different, then you can't have anything out of this universe but energy, of course. And so we're lucky we live in a universe that forms, for some reason we have matter rather than nothing. And secondly, we can form complex atoms, and atoms can self-assemble into all sorts of things, including DNA and our genes, and our existence to all of these things.
Мимо проходила
That's not
интересная
guaranteed in
история.
any particular universe. It's just that we're here to think about it because we're in a universe where this is possible. But lots of other universes may not be possible. So perhaps dark matter isn't dark matter, but it's another universe going through our universe, and the gravitational influence may be felt from this other universe. It may be something like that, which is why we can never detect this damn stuff. So that's about as complex as I want to make it.
Да,
I don't want to do
короче,
maths,
одна
even though I
вселенная
love
проходит
maths.
через другую.
And you don't want
Я
me to
ничего не
do
понимаю.
maths. So, if you have questions, I will attempt to answer them. Sorry?
You'll try to answer them without maths.
Yes. Look, electrons are great things. Hold on. Electrons around atoms. See, if I press on this wall, most of my atoms are empty space. Most of the atoms in all the wall are empty space. How come
Вот
my
смотря
hand
что я
doesn't pass through the
захочу.
wall?
Там еще можно
When everything is
смотреть,
so much full of
телескопы
empty
пойти.
space. And the reason for that is electrons. The electrons in my atoms repel the electrons in the atoms in the wall, and I can't pass through it. And that's how it works. That's why we don't fall through the earth, because of electrons. All of chemistry is just due to electrons. Every chemical reaction we have, every process we have, the DNA we have, everything we have is just because of electrons. Go on. Sorry.
Last two questions. How's the Big Bang created, and how was the universe heated up in 3,000 years?
Okay, so no one knows how the Big Bang was created. The suspicion is that it was a quantum fluctuation of the vacuum. That doesn't help you though. It's just a chance fluctuation in the vacuum that creates the universe. Now the universe in the first millionth of a second wasn't 3,000 degrees, it was several billion degrees. But by the time it cooled enough, expanded enough and cooled enough to be 3,000 degrees, that's when atoms could form and that's when light could get through.
Was Big Bang created by God?
No one knows. No one knows. It depends. Yeah, no one knows. And what was before the Big Bang? Nothing. The universe didn't exist before it. So it's as simple and complex as that, but that doesn't help you.
Question, when the Big Bang just started, it was very hot, these millions of degrees. How can we...
How come you know that?
I think that temperature would exist there. I don't know.
So remember I said there was a quark gluon plasma at 1 millionth of a second after the Big Bang. So let's go back a minute. We're all familiar with the nuclei of atoms. They're comprised of protons and neutrons in the middle of the atom and surrounded by electrons that go around them. But it turns out that protons and neutrons are not fundamental particles. There are things inside them that make protons and neutrons, and these things are quarks. And the two quarks that operate in protons and neutrons are things called up quarks and down quarks. There's two ups and a down in a proton, two downs and an up in a neutron. They have fractional charges, and quarks, in order that they don't fly apart in a proton and a neutron, are held together by what's called the strong nuclear force. That's just the name they give it. And the strong nuclear force is mediated over very short distances by these things called gluons. So the gluons are exchanged between the quarks, and they keep the three quarks together inside of a proton and the other three types of quarks together in a neutron. But if you start to increase this temperature more and more and more and more, the collisions between these things become harder and harder, and the quarks come out, because the collisions with ever-increasing temperature come out from inside the protons and the neutrons, and the gluons come out from in there, and so you've got this plasma of just quarks and the force-carrying gluons all around them. But you need billions of degrees for this. However, at CERN, they have created a quark-gluon plasma. They've got so much energy that the temperature of these collisions gets so hard that they actually smash protons and neutrons apart and create this kind of quark-gluon plasma. So we know how to make this, and it does exist. They make it all the time at CERN. Yes?
Is it possible to remove electrons?
Is it possible? Yes. It's called ionizing. Look, here we go. Let's do some chemistry. So there's two elements we could be interested in. One is sodium, and the other one is chlorine. Now sodium has a number of electrons, but in the outer shell it only has one, and it doesn't like only have one on the outer shell, because it says, oh, it kind of feels unstable. I want to get rid of an electron. I want to get rid of an electron. Hold on. And the chlorine atom has got one missing in the outer shell. And so the chlorine's always saying, someone give me an electron, someone give me an electron. I feel better if I have one more electron. Give me an electron. And the sodium's saying, someone take an electron, someone take an electron from me. And so when the two meet, the sodium gives up an electron and the chlorine takes it. And now the sodium lost an electron. And so it's now positively charged, and the chlorine atom has one more electron than it started with, and now it's negatively charged. And that makes salt. And there's so much salt on the earth. This process happens so often. They're so attracted to each other, these things, that once they're attracted, they never come apart again, because they're just bonded together. They love each other. Take my electron, take my electron, give me an electron, give me an electron. And so they're bonded this way. And if you look in the ocean, why is it salty? Because there's so much salt on the earth. Because as soon as these things meet, they never come apart. Yes?
So if I put the mixture on this chair, then I would be able to walk through this chair?
No. It's the electrons that stop you walking through the chair. The electrons orbit every nucleus of every atom that you have. Even though the atom is mostly empty space, the electrons are the ones that resist you going through the chair. The electrons in the atoms in the chair and the electrons in the atom in me feel like they're really firm. They push each other away. Otherwise, we'd all fall through to the centre of the earth, right? And we're not doing that. And it's because of electrons that we don't do that. Electrons do so many things.
And back and back and back until you die.
Yes, until you die. And even after that, you've still got electrons.
So then they'll still be falling to the earth?
Electrons will exist forever. See this light here? There's electrons flying through that right now. Electricity is just electrons moving between atoms along wires. Electrons do so many things. Even though atoms are all empty space, the electrons are the things that hold us all apart.
So, a question about dark matter.
Yep.
So you talked about the way that we can detect dark matter is from its gravitational effect, and potentially that could be from other universes.
Could be anything.
So,
yep.
Are there any experiments that we can use to confirm that, or is it all theoretical?
Okay. So the question is are there any experiments that we can conduct to find out what dark matter is, or is it just all a theoretical construct? Well, so there's no theoretical construct behind dark matter. There's only the observational evidence for it, right? There were galaxy rotation curves and gravitational lensing like this, right? That's the evidence that there's more matter than the matter that we can see. And about 5 times as much as the matter that we can see. So it's not like it's a little bit, it's a huge amount of matter. Now, scientists postulated that dark matter was made of certain particles. So it doesn't emit light. We can't see it because it doesn't emit any photons. So we can't see it in any way like that. And it doesn't emit any of the particles that we're familiar with that we can detect. So the two favourite candidates for these things are things called axions, which are lower mass things, and things called WIMPs, which are weakly interacting massive particles. But, as I said, I've heard people tell me all about detectors that they're going to make to detect this kind of dark matter particle or that type of dark matter particle, and they've spent lots of money making these detectors, and they've detected 0 particles of any dark matter so far. So I think, unfortunately, saying this thing dark matter, it's a bit of a marketing term. It just means we know nothing about it, right?
So this is gravity and we don't know where it comes from.
We don't know where it comes from, exactly. This is gravity and we don't know where it comes from. And it's not like it's an error in Einstein's equations of general relativity. because they hold up so well, doing lots of things, right? So it's not an error in that. It's just that there's some gravitational influence here, whether it's some kind of particles that we don't know about, or whether it's a universe passing through our universe. Something is having this gravitational effect.
Something in a dimension that we can't perceive.
Perhaps. Perhaps it's something in a dimension that we can't perceive. Exactly right. So we don't know what dark matter is, but we know no one has found any of it so far. And they've spent a lot of money making detectors trying to find it. Yes?
What's on the other side of a black hole? Is it like parallel universe, or could it work as like a reflection of our universe? And if you put your mind to it, could black holes lead to like time travel or whatnot?
Okay. Well, let's do the second bit first. Can you time travel through a black hole? No. You're going to die if you go through a black hole, right? One of the real problems with most black holes, almost anything has rotation. Galaxies have rotation, the Earth rotates, the Sun rotates. Wait a second, everything rotates. So everything has kind of this rotational energy. Now, if something forms a black hole, it will have the rotational energy of the things that went in there to form the black hole. So usually black holes rotate. And what many people who think about black holes don't think about is that black holes are so dense that they rotate space-time around with them. They drag space-time with them. And the closer you are to the black hole, the more space and time gets dragged around with it. The further away, slightly less. So as everything approaches a black hole, it's going to start to rotate, because as it goes closer, it goes faster, and then it goes in a straight line a bit, and then slower and faster and slower and faster and slower. And so it does these kind of rotations around the black hole, and the rotations increase in speed and emit radiation until finally they start to climb up the black hole, and then you get these giant jets that come out of black holes, right? All the big active black holes have got giant jets coming out of it. The one in the Milky Way hasn't, because it's quiet at the moment, and it's only the one in the Milky Way. There's a black hole in the centre of the Milky Way. It's about 4.3 million times the mass of the Sun. So it sounds large, but in terms of galaxies, the Milky Way is like suburbia. It's plain Jane of galaxies. As I said, the black hole at the centre of this isn't 4.3 million, it's 36 billion times the mass of the Sun. So it's a gigantic black hole, and that drags space a lot more around with it. But if you were to try to go into a black hole, the first thing you're going to find is that you die a long time before you go there, because the tidal gravitational influence is so great. The closer you get to it, the more the gravity is than further away. And at one point, from your head to your toe, is going to be so different in terms of gravitational force that it's going to actually stretch you like this and will kill you straight away, even before you get there.
Could stars and planets survive it, or is it?
No, nothing survives entry into a black hole. The only thing that's left is the imprint on the event horizon. So outside of a black hole, there's a thing called the event horizon. Within there, gravity is so strong inside the event horizon that even light can't get out. So the event horizon is the last imprint anything has that entered the black hole. So they're not survivable. Shame, right? Would have been a great story. Yes?
You know what a wormhole is?
A wormhole? No, I don't know what a wormhole is.
It's a hole that a worm made. It's like when two time tunnels connect.
Yeah.
It's like tunnels through time.
Yep.
So
I don't know that anybody has ever discovered a wormhole. But they have, now this is important, they have discovered time reflections. Time, we're mostly familiar with time that goes forwards. But there are quantum mechanical processes where time actually runs backwards. So in other words, you can detect a photon before you emitted it. because the time runs backwards in those reflections. And people have done experiments to demonstrate this. Even though it seems counterintuitive that this should ever happen, but there are instances where time does run backwards. As strange as that sounds. But no one's discovered wormholes.
So how do they know if if wormholes and dark matter are not discovered yet, then how are they known to be real?
Well, no one knows that wormholes are real, but people think dark matter is real because they can tell it from its gravitational influence. Like this. How it distorts those images. It looks like a gravitational lens, but it's just the severe influence of gravity that bends light. Right? I know you're not. That blue thing there is a galaxy. It's a spiral galaxy like this, way behind that thing, and the light just got bent around it so that it formed a ring around it. So the influence of gravity is very real. But it's much more influence than the matter that we can see. And that's the problem. But no one has detected any of this extra matter. Yep.
You were saying before that you thought universes are created from black holes.
No, our universe is very probably inside a giant universal black hole. I think. We live in a black hole.
So do you think that like the matter that gets pulled into a black hole is forming the energy?
The matter that gets pulled into a black hole just forms gravitational energy, gravitational influence. There's a famous case that there's a gravity wave detector in the United States called LIGO. It's basically a right angle arrangement where each arm is several kilometres long. And there are mirrors at each end, and they shine lasers down these things, and then they get an interference pattern in the middle, so they can tell whether any of these lengths change. In minute detail, any of them change. And they do sometimes when gravitational waves pass through the Earth. And they can measure these. And they've measured two black holes merging somewhere in the universe, and they measured the gravitational waves and the influence of how they lengthened and shortened each of these things when the waves pass through us and through the Earth. We can't feel them because they're very weak, but with this detector I can feel some gravitational waves. Now, there are people who think that at the start of the universe formed, as well as that picture of the microwave background, they formed gravitational waves. And that's probably very real, I think. If we're going to have a universe which contains all the matter in the universe and is the size of a pea, they're so dense, that's so much matter in there. First of all, it's going to make a black hole, and secondly, it's going to release huge amounts of gravitational waves throughout the universe. So we should be able to detect these, but not with the detectors that we have now. We need a detector with arms like from the Earth to the Moon.
So the conservation of energy theory, that means that there can't be any more energy or matter coming in, can there?
No. There's no evidence that there's any more matter coming into our universe.
So any matter just...
So we've got this amount of matter and this amount of energy, and the universe is just eventually going to wind down slowly and die a death from no more energy in the future. Energy will just dissipate. In other words, entropy will increase. Entropy is just the disorder of things. Yeah. Time won't matter anymore because there won't be any energy. There'll be no energy. We use energy all the time, right? We use electricity, that's generated from energy. That energy source is not going to be there in the future, right? So we can't make electricity in the future, so we have to go somewhere else because there will be an energy death here. In other words, entropy will increase, disorder will increase. All processes increase entropy. There's no way around it.
So what happens to individual galaxies? So if all the galaxies are moving away from each other at an increasing rate, eventually we won't see any other galaxies.
Ah. So the question is, if all the galaxies are moving away from us at an increasing rate, the further away they are from us, eventually we're not going to see those galaxies. Exactly right. They will go beyond our visual horizon, and we won't see them. Apparently, now the theory is that there's lots of the universe that we can't see because it's already beyond our visual horizon. They think the whole universe is many times the universe that we can actually see.
And what will happen to the stars in our galaxy? Will they move away from each other?
No, the stars in the galaxy are gravitationally bound together.
So does that
It's like the planets around the sun, right? They're gravitationally bound to the sun. It's like that globular cluster that you saw there in M22. Those 100,000 stars are all bound together gravitationally, so they're not going to come apart because the local gravitational influence is so strong. It's like a black hole's not going to come apart, right, with the expansion of the universe because its gravitational influence is much stronger than the expansion.
So the state of the Milky Way will just stay the same?
With the Milky Way will just stay the same, but lots of other galaxies will recede further and further and further and further away from us, right?
And eventually
That's
the
what
stars run out of energy.
Yep. So what happens in the end depends on the shape of space, whether it's positively curved or negatively curved. So, I need to explain this now. How can you have three-dimensional space being positively curved or negatively curved? Well, let's do positively curved first. Let's imagine we have two-dimensional space. Let's imagine it's a flat plane. It's like a giant piece of paper, and all the critters on there are just flat, two-dimensional things on that piece of paper. Now we can see if the piece of paper is just flat, and one of them's got a laser and fires it out that way, then it just goes on forever along that piece of paper. But instead of that, if the two-dimensional beings, instead of being on a piece of paper, are on a giant sphere, a giant balloon, then they can't tell that there's any other dimensions inside, because they're just two-dimensional objects, right? But if they shine a laser down this way, the laser will eventually go right around the balloon and come back, and they'll be able to see it. Oh, there's my laser, right? In the same way, in three-dimensional space, if the space is positively curved, then you can fire a laser this way, and it will actually diverge in every direction, the laser, because the space is curved. It will just form a cone and go right around the universe and come back. Oh, there's my laser, right? You won't be here to see it because it's so long. It will take so long to go around travel around the universe. But that's a positive curvature. Comes back on itself. Negative curvature, if we think about a two-dimensional object, is like a saddle-shaped thing. It goes this way, and it goes that way, and it goes that way forever. And so you shine a laser that way, it disappears. Never see it again. And so it all depends on whether our universe, what curvature it has, as to what future it's going to have. If it's got positive curvature, eventually it will collapse again. And like running our movie backwards, it'll run the movie backwards and it'll explode again, presumably, because it'll form another singularity and start again. So the hope is that would happen, but nobody will survive.
So does the fact that galaxies are moving away from each other at an increasing rate mean that the universe has a negative curvature?
No, it doesn't. If we think about, so the galaxies moving away from us at increasing rates over distances, does that mean that it has a particular curvature? Not necessarily. If we think about how we blow things up, think about the two-dimensional analogy of the balloon, right? We've got two-dimensional beings on there, and if we blow their universe up, then it gets bigger and bigger and bigger and bigger, and things close together don't go far apart very fast, but this one and this one, along that axis, go apart very fast as we blow the balloon up. But yet we know the balloon has positive curvature. Yeah, so this is a hard question to answer about our universe. It looks like it's flat. like a piece of paper. As close as we can guess, it's flat. Doesn't have positive or negative curvature. It's the weirdest thing. Yes, mate. Not wormholes again, right? No, good on you.
Did scientists predict that at least in Google years that there will be nothing left for the planets will stop spinning and there will be no time?
No, the planets won't stop spinning. Things won't stop spinning because that's the conservation of momentum.
No, like the Earth will, the universe will run out of energy and then...
The world will run out of energy, but it won't run out of momentum. Momentum's always conserved and energy is always conserved, but the energy is redistributed so evenly that it's unusable in the future. Everything will have the same energy, and therefore, if there's no difference in energy level, you can't use the energy because it's all at the same level.
But scientists predict that in more than Google years, which is a one
Google years.
more than 100 zeros.
Yes.
The planets will stop spinning and...
I don't think scientists predicted that because if they predict that, they don't know about the conservation of momentum. And they should know about that. If they don't know about that, then they need to go back to science school, right? Yes?
Simple one, I guess. People put some satellites up there. Apparently, the time goes at different speed.
Oh yeah. Oh, that's Einstein's theory of relativity. So let's imagine, here's a little experiment to think about. Let's imagine we get in a spaceship, very, very fast spaceship, and we travel at about 3/4 of the speed of light. At that speed, time is going to run at half the rate. So imagine we've got a light on our spaceship, right? And we count our heartbeats on the light. And we on the Earth look at this thing and it's going 3/4 of the speed of light and say, his bloody heart's going at 30 beats a minute. It's just really weird. What's going on with this thing? 30 beats a minute. It should be 60, right? Normal human beings run at 60. But you're on the spaceship and your heart's beating at 60. And you can measure it. And you've got a watch and everything runs okay and you're measuring 60. We're seeing 30. So what happens? So we see 30 beats a minute and you go from here to Alpha Centauri and it takes you 5 years, for instance, at 30 beats a minute. So we know how many beats your heart is going to do from here to there. But you think 60 beats a minute. My heart, there's nothing wrong with me. I'm normal. But when you measure the distance to Alpha Centauri, you don't get 4 point something light years, you get 2 point something light years. The distance is different. You measure distances differently. At that speed, you measure half the distance when your time is halved. And these effects are real. There are particles, there are cosmic rays that hit the upper atmosphere, right? And they form certain particles that rain down on the Earth. Now, these particles go very fast as they come down to the Earth. So fast that they run slower time. If you stop these particles and measure how long they live for a very tiny amount of time. But yet they've taken so much time that they can reach the surface of the Earth and we can detect them here. Why can they reach the surface of the Earth? Because they go so fast, their time is slowed. So they reach here before they die. So these effects are very, very real. So that's the effect of speed. There's also an effect on time of gravity in the same way, and accelerations. And that's general relativity. That's much more complicated than uniform motion. But the effects of uniform motion are counterintuitive. Strange things happen in the real world. We live in an interesting place, right? All right, great.
Thank you very much.
Great. Yeah, you asked a lot of questions. Look at this. Good on you. And wait. One of these to decode it with. Good on you.
Thank you.
Okay.
Thank you.
All right.
Good.
Thanks a lot.
What's your day job? How do you know all this? Something to do with you?
Yeah. Look, I'm a computer scientist by training.
Yes.
I spent 40 years working on AI.
Oh, right.
Yeah. But I like
Я сама тут
science.
просто
I like
чуть
physics.
с ума не сошла,
Yeah, I
прослушав
studied a lot of
лекцию
physics and I like physics. Yeah.
про электроны,
But a lot of scientists
и все
tell you a lot of
остальное.
things
Ничего не
like
понимаю.
they're confident that this is going to be it or whatever it is, and then suddenly, oh, they're wrong. That wasn't right. Yeah. I love those moments.
That was a really fascinating talk.
Thank you so
Oh,
much.
no, that's okay. I'm glad you enjoyed it. Did you enjoy it?
Oh no, because I don't understand anything.
You don't understand anything?
Yeah, English not good, and it's like universe. You said everything that's coming to a black hole, it just disappear. Yeah, it's like
Yes.
you can't survive.
No, but we're inside one that's as big as the universe, I think.
Yeah, but if you say also we are like in black hole now.
Yeah.
The universe inside the black hole.
Really?
How we survive?
Because it's so large. It's so large, the effect is so small here. It's so large.
It's very hard to understand.
It is very hard to understand, but it seems to be unavoidable. Did you enjoy it?
I did. I just have a few questions.
Yeah, go on. No. I hope I can answer them.
Things pop up. So, what I want to know is, what are they doing at CERN? Because I know that they're getting the
Yeah,
collision happening thing.
they are.
Why are they doing that?
Because they want to try to understand how the universe operates.
Okay.
So at the moment, their energy is so high
Yep.
that they've created this thing called the quark gluon plasma, right?
Yep.
So they're at 1/1,000,000th of a second after the Big Bang is when this happened, this quark gluon plasma happened.
Yeah.
And they have so much energy that they can recreate what happened 1/1,000,000th of a
Is that
second.
in Melbourne? They're doing that?
No, it's in Switzerland.
In Switzerland.
It's a thing that's like 27 kilometres long, the accelerator. It's the biggest accelerator on the Earth.
I think they've got a smaller one in Melbourne.
В обсерватории я сейчас нахожусь, пытаюсь понять, что они говорят.
I swear I heard that. Yeah.
So
Yeah.
I know the person who first discovered quarks.
Oh.
Yeah, he worked at SLAC, it's the Stanford Linear Accelerator Center,
Yeah.
and he was the first guy that reduced the data that actually found evidence for quarks. Because the guy that theorised that quarks exist was another guy from Stanford who won the Nobel Prize for that theory.
Yeah, that was really interesting, that bit. The way I was kind of thinking about it, I was thinking about it in the sense of the physical body, so the healing of the physical body and the breaking down of the physical body and things like that, because of the donations, I think, of the electrons and different things like that. Yeah, that's when you were talking about the planets, I was putting it into like that kind of...
Yeah, well, we're all made of atoms.
Correct,
right?
yeah.
Which are mostly empty space.
Yes.
Really weird.
Yeah.
But the things that hold us up and that makes us all function and holds the atoms apart are electrons.
Yes. Yeah. And
All of chemistry is electrons.
Yeah, and the different like the donations of the atoms and the electrons and protons and things like that. And sometimes when you're feeling like more energized, and then you'll be around people and then they'll make you feel less energized or more energized. And I think that we're donating.
You think so?
I do. Yeah.
Okay.
Да, это в центре, ну не совсем в центре, это в одном из уголков Сиднея. У нас много обсерваторий, и каждая обсерватория наделена своими объектами, которые изучают. То есть нужно наблюдать именно какие-то объекты, которые закреплены за этой организацией. То есть кто-то наблюдает одну там часть Вселенной, кто-то другую.
I guess websites that have like updates of all the stuff, like as it comes out. Like how do you keep up to date with it all? Because I mean, there's constantly new things coming out about.
There are constantly new things coming out. For instance, just recently there was a paper came out.
Yeah.
You know, there are 2 pointers to the Southern Cross, Alpha and Beta Centauri. So Alpha Centauri is a double star, right?
Yes.
You would have seen it in a telescope maybe. It looks like 2 headlights coming out of you. Well, they're just recently discovered that it's a planet orbiting around both those stars.
Yeah, which we had no idea.
No idea that there were going to be planets orbiting stable orbits around two stars that orbit each other, right?
Yeah.
Yeah. And so that's just recently.
Yeah.
So you have to read a lot of research.
Yeah.
You have to keep up with the research. So I'm flooded with research.
I know, yeah.
So stuff that I want to read,
yeah.
and the stuff I'm interested in, because I'm a computer scientist and I worked on AI for a long time.
Yeah.
So I still read those research papers.
Yeah.
Then I've got research papers that my daughter and my son-in-law feed me on.
It's like overload.
You
have to pick. You have to pick
on other stuff that they do, which is biology related.
Yeah.
Like, and I'm not a biologist, and I've got all these crazy acronyms in their papers, and I have to go back all the time. What does that mean?
See, I like to think of this kind of stuff and then link it to biology. I think that's interesting.
Yeah, well, biology is all a product of electrons.
Yeah.
Because it's all chemical.
Yes.
It's all chemistry.
Yeah.
Biology is just chemistry.
Yeah. And it's interesting, like I even think like when you go into the medical kind of field, I think we're still we're in the Newtonian, but I feel like we should be more in sort of the exome squared stuff.
Well, no, there's no doubt. Newton only works for really
Может, они
low
прилетели,
speed
но поняли, что тут делать нечего, потому что люди еще не доросли.
As soon as you start to have gravitational fields, as soon as you start to have fast travel, all this kind of stuff, I mean really fast, sometimes a multiple, close to the speed of light, then things are going to go really, really different. Newtonian mechanics breaks down. The first validation of Einstein's theory was done in the 1920s. A guy called Arthur Eddington led an expedition into Africa because there was going to be a solar eclipse there. So what they measured was the position of certain stars close to where the sun was going to be in the sky at that time. And they mapped them all precisely. Then when they had the solar eclipse, they started to map the positions of the stars right around the solar eclipse. And they found that they were seeing stars from behind the sun. Now, Newton's gravity predicts that the gravity will actually bend the light of those stars around the sun. But it predicts only half as much the bending as Einstein's theory does. And Einstein's theory was the one that was right. Now, Einstein never did a single experiment. He just thought out this stuff by making the world consistent. And it has to be this to make the world consistent.
Yeah, and you said that as time goes on and everything sort of loses energy, everything becomes the same plateau of energy, if you will. So there's no like donation of any...
There's no energy to exploit.
There's nothing.
There's nothing.
There's nothing, it's just like... And you said that everything's in a state of breaking down.
Entropy increases.
Yeah.
So that's thermodynamics. If you study thermodynamics...
Is there any cases where that's not the case?
No.
Because that's the question I wanted to ask.
No.
Okay.
Every process that we have, every physical process, every chemical process that we have, always increases entropy, increases disorder.
And because what they're looking at, obviously, with the way we age and everything now, I'm just going into that, is like they're trying to slow that. So how do they slow? They're thinking, what can we use to slow that? You know, which is quite interesting. What new research might come out about that, and if that correlates to anything, like, you know.
The problem with stopping aging is thermodynamics and entropy. We always increase in entropy, right? We always make more disorder. I've got more disorder than you have. I'm 70. So my body's got a lot more disorder than yours because I've just been around longer.
What about the cases where someone might be like a healthier though than?
Oh no, you can be healthy and you can go out of your way to be unhealthy.
Yes,
so you could be unhealthy.
So there could be more.
But it's just the growth in disorder in general cannot be halted. Okay. Every process increases disorder and increases what's called entropy, which is a measure of disorder.
Yes.
Yes.
So interesting.
I know.
Interesting. Yeah. I think
the universe is a weird place, right?
It is.
We think we're all in charge of everything and everything's going to be okay, but in fact we're all just
flying somewhere.
Pawns in the game of the rules.
It's scary.
Even they look at the clock. I don't know where there's a clock, and one person reads it, and another person reads it, and it's one slightly, you know, the wave. Particle theory. You know, one person sees a wave, another person sees the particle.
There are great experiments about that.
Love love that.
There are great experiments about that.
Yeah.
So, there's an experiment that you can do. You know the double slit experiment?
Oh yeah, we either look through the.
So you can you can shine a light through a double slit.
Yeah.
You have a screen at the back and you get an interference pattern, right?
Yes, yes.
The interference pattern there. So you can do this with electrons.
Yeah.
You can take an electron gun.
Yeah.
And you can make two double slits and a screen at the back,
Yeah.
and you can shine the electron gun through the two slits and you get an interference pattern at the back, right?
Yeah, yeah.
Now, you slow the electron gun down so that it only emits one electron at a time.
Yep.
You emit an electron, you figure out where it landed over there.
Yep.
Emit another one at the double slits, figure out where it landed over there. And by the time you've emitted thousands of electrons and figured out where they come over there, you've got the interference pattern again. So each electron goes through both slits.
Yeah.
Because that's the wave nature of electrons. Now, they did another experiment. So what they do is behind the slits they put a detector.
Yep.
Did it go through both slits or not? And so they start to do this experiment again with one electron at a time. And now it only goes through one slit. The detector says, oh, I went through that one. The next detector, went through that one, went through that one, went through that one, etc. But now when you look at where they landed, the interference pattern's gone. There's one there and there's one there. No more interference. Because by measuring here we change the downstream universe.
Amazing. Amazing. Amazing.
So by looking at stuff and observing stuff, we change the universe.
That's
Yes, and that's scary because when you start just talking about the chairs, you can't get through the chairs. I mean, think if you said it's moving electrons, it's like I'm being afraid it can disappear now because
no, it won't disappear. Has it ever disappeared throughout your life?
I always think of it like it's energy, but it's oscillating and vibrating at different rates and very slow because it's dense and heavy. And if it's
the heaviness is due to the protons and neutrons.
I'm afraid it's like
electrons weigh next to nothing. Electrons, the weight of the atoms are just the protons and neutrons. The electrons, they weigh thousands of times more than electrons. Electrons weigh next to nothing. But electrons are the things that stop us going through the chair.
Wow. I think in the future medicine will be around electrons. You watch. You'll say this crazy lady I saw once. In like 10 years you'll be like that lady. Yep. You watch. You'll get cold and you'll go and get a donation of electrons from the doctor. For sure. For sure. For sure. Thank you.
It's an interesting universe.
It sure is amazing.
Yeah.
Where do we send questions? You got an email address? I've got plenty more questions.
She does not want your contact.
It's going to be like, yeah.
You have to read.
Okay.
You have to read.
Yeah, and do the
Google some stuff.
ChatGPT.
No, not ChatGPT. No. Find out your own information. You don't need it feeding you crap.
Yeah.
Find your own information. Just whatever you're interested in about the universe. There's lots of stuff around.
Amazing. It's been eye-opening.
It's not always straight away you can find true, you know. You sometimes think it's true, after that you find some opposite things. It's like confusing.
Yeah.
Very difficult.
There are lots of problems we don't understand, right? As a species, we don't understand lots of problems.
Yeah.
Dark matter is one thing we don't understand, right?
Absolutely.
Yeah, there's lots of other things we don't understand. Consciousness we don't understand very well.
Yes.
How does the brain do consciousness? Which neurons are involved in consciousness? Which part of the brain does this stuff, right?
Yeah.
We don't. There's lots of things we don't understand.
Exactly.
It's amazing.
We just learn, you know, going through the life and learning.
Yeah, that's exactly right. That's exactly right.
Something happened in the upstairs?
No, I don't know. You can have a look if you want.
There was some line, some people like.
Oh yeah, you can probably go through the telescope now. There won't be any lines.
Okay, very good. Thank you. See you. Thank you very much.
Because they told it
Amazing.
Straight through. Yeah.
Hello.
Hello.
There is something upstairs happening?
Yep.
Wow.
Looking at the moon.
Wow. Not on the stars, just moon?
Just the moon.
Okay.
Perfect one.
And also we have more aperture. So we put more photons and magnify them. So these photos you see down the bottom, the one at the top's got a
Я специально долго ждала и слушала эту лекцию, хотя ничего не понимала, потому что была очень большая очередь посмотреть в телескоп. Сейчас можно. Крышу открыли, телескоп установили. О, я могу видеть Луну, прикольно. Ух ты, ух ты, ух ты, ух ты. Trying to find out.
And there's a mountain in the middle of the top.
basically just
Можно посмотреть.
From those along the shadow.
Через камеру тяжело.
Between the dark and light zone, there's a big flat area. That flat area is the Sea of Tranquility, and that's where the first people who landed on the moon landed.
Нет, глазами лучше смотреть. Там смотрят на Луну.
So when we look from little telescope, yeah. So when we look from little telescope, with a big telescope, it's got more focal length. And so
You'll be able to see three big craters.
Very important attribute is the aperture, so the size of the hole.
Top crater's got a mountain
detail.
Yeah.
So
That mountain's 2 kilometers tall, and that crater's 110 kilometers across.
You'll see 3 craters here. One of the top has got a mountain in the middle.
Ah, yes.
Yep. And you guys as well.
Wow.
So we're going to look at a view like this, with a mountain in the middle of this crater here.
Yeah.
Yeah. That crater is called Theophilus. It's 110 kilometres across. The mountain is 2 kilometres high. Above that, you can see there's a mountain range sticking out in the sky. Above that, where the writing is, that's where Apollo 11 landed.
Is this where we go? I didn't come up here. Is this the right way, Carl?
So where the writing is where Apollo 11 landed.
Don't put the flash on. No. Don't put the flash on.
So are we looking at where Apollo landed?
Do you want to be in the photo?
It'll look like this through the eyepiece.
And the name of the sea is the
Sea of Tranquility. That's this one. So
oh yeah, so it's the big.
Yep.
Two
It's
eyes.
it's the face of the rabbit.
Yeah.
Yeah. So Apollo 11 landed where the ear joins the face of the rabbit.
Yeah.
Just here.
Face of the rabbit. So
Cool.
интересно. Thank you. О, какой огромный телескоп.
Around this way, please.
And Jonah.
How you going, mate? Good. Are there people behind you? Just us two here. Really? Nobody behind you? No. End of the queue.
Прикольно. Открывается крыша, и вот можно смотреть на Луну через такой большой телескоп. Смотрите. А тут просто люди живут кругом.
We came out about probably 6:30.
The top one's got a mountain.
So we just went out dinner.
How tall would the mountain be? Like
That mountain's 2 kilometers
Look
tall.
at the telescopes. These two telescopes.
So that's
No, we just got here now.
just
Yeah,
the same
just
height as the tallest mountain in Australia.
Just going to the top.
So that's why we got here probably 6:30 and just went around. It's just
Sure, what you're saying is the right human waiting.
Last year, Saturday night, the queue to get to here was 2 hours.
Whoa.
And we were still showing people at 11:30.
Wow, that's crazy.
Supposed to finish at 10.
So I can talk to you guys at leisure.
Oh, I came to this course here about 3 years ago. Yeah.
No,
We did a 6-week course.
8 weeks.
Oh, 8-week course. That was,
Yeah, it's good. I know the lecture's great.
yeah. It was, his name?
Yeah, it looks like really again like snow around. Oh, so nice.
So that's it for
Seems very well.
There's no more people.
No, seriously, what's your name? Sorry? Craig.
Yeah, because I used to get emails for the
Unfortunately, I don't see nobody there. Офигеть, какой классный большой телескопик. Так здорово все посмотрели, так пойдем вниз уже. Ой. Такое приключение в обсерватории. Здесь фотографии можно всякие посмотреть. И тут куча всяких галактик и других фотографий. Там тоже всякие телескопы. И наблюдают галактики.
Okay, so everyone, take whatever you want home, enjoy. Enjoy. And thank you. Thanks for what you've done. Alright.
Hello.
Good job, Alex.
Thank you.
You're a legend, man.
Oh, you like images?
Yes, it's so amazing. It's like you can't understand what is it and how far it is.
Yeah, that's right.
Wow. You still didn't catch anyone who moving somewhere? No? No? No any signs, no signals, nothing?
Not yet.
How it can be?
I know.
They hiding?
Yeah, I know. I know, it's strange, isn't it?
Really strange.
Yeah.
So many galaxies, so
Yeah,
many stars.
So many stars, so many planets.
And planets, yeah.
Shall we get them in?
Ooh.
Shall we get them in?
Thank you for great show.
Oh, okay.
I'm leaving here for,
Yeah, okay.
yeah.
That's great.
Sometimes coming, yeah. And I see so many cars today. It's like big event, yeah.
Oh, yeah, it's a big event. Once a year we do this.
Oh.
Yeah.
When
Usually people here every Thursday night.
Thursday night. But
Thursday night.
sometimes it's like raining. It's nothing seems.
No, you can't see anything if it's raining.
But people anyway coming.
Yeah, people come. We do things. We talk about stuff.
Ah, okay.
Yeah.
Maybe I can come sometimes.
Yeah.
From what time? 7?
7:30.
Ah, okay.
7:30 on a Thursday. Yeah.
Okay, maybe. Okay, thank you.
Hopefully you'll come.
I'm not first time actually here.
You're not first time, okay?
Yeah,
Good.
I've been, but it's been not a big event. I was
Yeah, okay.
just come to say hello because I've been wondering what's going on here.
Yeah. Well, now you know.
Yeah, it's like a bushy around everything.
Yeah, it is.
It's like,
Yeah, I
I didn't
know.
expect it here, something like really.
It's been here for a long time. It's been here for a long time. We've been added to it.
Yeah, I see some members like really many years here.
Yes.
Wonderful.
Yeah, I know. It's a great thing to do. I enjoy it.
Yeah, of course it's interesting.
Yeah, I enjoy it.
If you have time, why not? It's big fun.
Yeah, it's a lot of fun. I love it. I'm going to get a drink because I'm dying.
Of course.
We've got Coke and pumpkin. What would you like? Coke. All right. Thank you. Thank you, Mandy.
Okay, have a good night.
Okay, good night.
Okay, good night. See you. See you. Bye. В общем, я просто в шоке, народ. Какая красота. Вот просто как будто бы гараж и маленький домик. А что там происходит? Ай-яй-яй. Так, все, я буду заканчивать эфир. Если кому интересно, оставайтесь на связи. Коннектитесь в мои контакты. И будем еще встречаться и изучать звезды и не только. Вообще эту жизнь. И что в ней происходит. Всем пока!